Good morning, friends. This time to begin the class. Couple of announcements before we start doing math. Announcement number one, homework 2 will be out today and you'll get about a week to submit it. Quiz 2, we are planning to hold on either the evening of October 8 or October 9 or October 10. Obviously depending on your availability on that and the TA's availability. So if there are there any events already scheduled on these days? Events in which most of the class will be busy. Some other lecture, for example, some other quiz. Is there anything scheduled already? Okay, so apparently not. I'll check with the
Sir,
TAs. Yeah.
sir, can you just keep it on 8th or 9th and leave the 10th?
Why?
Sir, I'll be onboarding on the 10th of it, so it would be a
You
bit
have already
difficult.
booked your ticket?
Yes, sir, on 10th, most probably.
Okay, potentially there could be others who want it on who are onboarding on 9th. I don't know. Okay, fine, but I'll keep this in mind. Anybody else having any personal issue with any of these dates?
Sir, I have an issue on October 10th, sir. I am also onboarding on October 10th.
You are also onboarding on October 10th. Okay, so let's try to keep it 8 or 9. In case we have to keep it on October 10 and you miss the quiz, I'll allow you. I mean, assuming you give me a sufficient proof that you're onboarded on that date, I'll allow you to take the compensation quiz, which will happen at the end of the semester. That is like the worst case scenario, but I'll try to avoid that.
Just sir, if you keep the quiz in case, then what would be the expected time? I mean,
Expected what?
sir, the expected time.
That will depend on the TA's availability. That's why I'm not able to commit right now, right? I'll have to check with them. I'm pretty much free on all, so any time is fine with me personally. I'll have to check with the TAs.
Okay.
Okay. Yeah, I'll let you know. So this is just a quick heads up. In any case, you'll get the final announcement of the quiz at least 1 week before the actual quiz.
Sir, on October 9, I think some people have their COL 106 lab.
Why on October 9 do they have their lab? It's a Saturday.
Yeah, I checked
Yes,
on
right,
this
people.
night. Yeah,
Sorry?
but it's on Saturday, class 9. On 8, there's some presentation, so no classes.
8th, there are no classes. Who told? I didn't see that in the
No.
academic calendar.
No. There's no call 106 class that day because
There
of
is no
midterm
call 106
presentation.
class on October 8.
Yeah.
And it is going to happen on October 9, is it?
Yes.
So we can use the call 106 slot for our exam on October 8.
I think.
Or what is the call 106 slot? F, right?
I don't remember.
Yeah, I think it is. Okay, fine. So let me just note down for my reference. So some students onboarding on October 10th potentially, and then there are some. Okay, so potentially call 106 class/lab on October 9. So I'll find out from the call 106 instructors. Whom should I find out from? Professor Bakchi or Venkata sir? Whom should I ask? Who is teaching these days?
Professor Bakchi.
No, sir,
Okay,
Venkata
fine.
sir. Actually, Bhakti sir had the last class. Just the last class was Bhakti sir's last class.
I see. Fine. I'll check with yeah, Venkata then. Okay, I'll find out what is the time and then I'll ensure that it doesn't conflict with our quiz. Okay, fine. So this is some work for me. All right. Okay, I hope the recording has started. Yeah, it has started. Cool. Somil, you have your hand up already.
So I have a personal issue with October 9 evening too. Like I'll be organizing a quiz that day, like a quiz in the quizzing club since. So yeah, so that's not like important work, but yeah.
Yeah, I cannot take this into account, unfortunately.
No problem.
Yeah. Okay, fine. Chalo, so what we were doing last time, we were analyzing this the simple question: how many ways are there to distribute n balls into m bins? And then we looked at several about 8 scenarios, right? So whether the balls are distinct or not, whether the bins are distinct or not, and whether you are allowed to keep bins empty or not, right? So depending on all of these choices, you had these 8 scenarios, and in some of them we got some nice answers, right? And then in the remaining 5 of them, we did not have a good idea of how to do it. So today we plan to do 3 of them, 3 of the remaining 5 open questions. So far, if I could call them open questions, and then the remaining 2, right, the ones in orange, we'll leave them for later, right? So they will require some technique which we are going to introduce in the next couple of lectures, and then we'll do them. Okay, so let us take this up. Let us take up the scenario where you have n distinct balls, m bins, and the bins are not allowed to be empty. No bin is allowed to be empty, right? And then in last class itself, we observed that this is nothing but the number of surjections from an n size set to an m size set. Okay, so now let's try to count them. Okay, so what do we want now? So okay, so we want to count number of surjections from an n size set to an m size set, right? So if you have, I hope you haven't forgotten, but let me quickly recap. So you have the set A of n size of A is equal to n. You have the set B, size of B is equal to m. Of course, the second this setting where no bin is allowed to be empty makes sense only when n is greater than or equal to m. Otherwise, the answer is just 0. Right? Yeah. So here we have n is greater than m. And now you want to find all functions of this form. Of what form? Functions with the property that every element of B has some pre-image. Right, so we want to count the surjections. Right, so now what are we looking at? So let's call let's call this set B to be this. Let's assume that this B is the set 1, 2 up to n. Right, doesn't hurt, right? What elements you have in the set really doesn't matter over here. Okay, so now what? Let's set up some notation. Let U be the set of all functions from A to B. All right. So from this set, we want to remove all the functions which are not surjections, all the problematic cases, right? And what could result in a problem, right? So if the element 1 does not have a pre-image, that is a problem. If the element 2 does not have a pre-image, that is a problem, right? So there are kind of m reasons for, right? So for a function to be bad, and if a given function does not satisfy any of these m reasons, then it is good and we want to count it, right? Okay, let me actually, just to be consistent with the future notation that I'm going to introduce, sorry, let me just rename these sets to x and y. So this is x, this is y, size of x is n, size of y is m. Vibhanshu is saying voice is breaking in between. Is that only for him? Is there anybody else who has an issue in being able to hear me?
I think
No,
it's
sir.
fine, sir.
It's fine. Okay, cool. Cool. Shrimanti, I'll announce the syllabus later, maybe in the next class.
Okay, sir.
Okay, cool. So what was I saying? Yeah. So U is the set of all functions from x to y, and then let AI denote the set of functions from x to y, right? So set of functions under which I does not have a preimage. Does not have a preimage. Right, so AI consists of all functions from x to y, with the property that the element I does not have a preimage. Nothing comes into I. Right, and then what do we want to count? We want the size of the set U minus A1 union A2 union AM. Right, is this what we want? Right, so we want a function, we want to count all functions which do not belong to any of the sets AI. Good. So how do we do this? Somebody mentioned some principle last time. Somebody mentioned some principle. I forgot who did. Who said that?
Sir, we will find it by the set theory. We will first find the union of A1, A2 up till AM, which is equal to the sum of cardinalities of all AI minus intersection of 2 plus intersection of 3 and so on.
What is this called? What is this statement called?
This is called inclusion-exclusion principle.
Inclusion-exclusion principle. Absolutely. Yeah. So that is what we'll use to find this. So okay, fine. So I think Vibhanshu, the way you have seen it is an expression for this guy, right? So we'll just derive the expression for this whole thing in one shot. Okay. Right. So yeah, so we are going to use something called the principle of inclusion-exclusion. So right. So we'll conveniently just call it PIE, pi. Okay. Right. So what is the principle of inclusion-exclusion? So let me write it as a theorem. Right. So let us keep this aside. Let us push this on the stack for a while. Let's state the inclusion-exclusion principle, prove it, and then we'll pop this from the stack and take it forward. Okay. Fine. So what is the principle of inclusion-exclusion? Let A1 through AM be subsets of a finite universe U. Then, right. So how should we do it? Maybe okay. Actually, let's leave this aside and let's see how do you do this, right? Let's understand the idea behind it, and then we'll state the. Or maybe let me state the result and then explain the idea. Fine. So then what we are saying is then the size of U minus A1 union AM, right? So this is equal to, right? So what Vibhanshu said is essentially what he said is you take the size of you subtract the sizes of each AI, then you add the sizes of intersections of 2 of them, subtract the sizes of intersections of 3 of them, and so on. Right? I'm just going to write that same thing in a more compact manner. Right? So what I'm so how do I write it? So this is equal to summation over all S subset of 1 through M, right? So let us take the intersection of all AIs such that I is in S, right? I'm looking at all possible subsets of indices of these sets, right? And then I'm taking the intersection of all the sets which are kind of indexed by the indices in the set S, right? And then I'm attaching an appropriate sign with it, -1 to the power size of S, right? So observe that this is same as, so this is same as saying summation over k equal to, yeah, so what could be the possible size of S? The size of S could be anything between 0 to m, right? Summation over S subset of 1 through m, size of S is equal to k, right? -1 to the k, same thing, intersection I in S, yeah. Okay, raise your hand if you had already seen this before. This is problematic. Okay, some people had seen this before. Oh, quite a lot of people have seen this before. Okay, let's wait for a couple of seconds and see how many hands get raised.
So you're asking about this principle or about this notation?
No, the principle.
Okay.
So the notation isn't a big deal, right? Yeah, okay, fine. So I can see that it's hard to count, but oh yeah, okay, 50 raised hands out of how many? Out of 94. That's cool. So more than half the class already know this. Okay, any issues with the notation? I am not sure whether you saw this. I mean, saw this principle in exactly this form before, right? I'm just putting it in more convenient notation instead of taking this summation over what? Summation over I1 less than I2 less than blah 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 less than IK something, right? So I don't want to make it so messy, right? So okay, you can lower your hands. No, I can see that more than half the class has seen the proof, right? Now, yeah, lower your hands and now raise your hand if you have already seen the proof of this. Raise your hand if you have already seen the proof of this. Okay, so 2 people have seen the proof. So yeah, definitely we should definitely do it then. Okay, right.
Sir, like, isn't this the expression of A1 union up till AM? Like, why did we write it equal to like number of U minus A1 U AM?
Sorry. No, I have. Okay, wait. Sorry, I should have said something. I should have said something over here. I should have added something. So here, for if your S is the empty set, right? S goes over all subsets of 1 through n. So if S is equal to the empty set, then we define the intersection of I in S AI, this expression to be U. Okay, or if you like, if you don't like this, or if you don't like this, what? Okay, so this, let's get rid of this actually. So yeah, let's do it in the following way. Let's move the things around a bit. Okay, right. Okay, so let me just make it clear. S is not the empty set. And then I'm taking the size of U minus this. Now is it okay?
Yes, sir.
Yeah.
So one thing. So if we are not taking S equal to 5, so would K equal to 0 be considered?
Same thing again over here. So K equal to, yeah. So what should I write over here? Yeah, I think I can easily modify this. Right, so I should make this K equal to 1 to M. Oh, sorry, I think I messed up. I should have written U plus, no? Right, because I have -1 to the power size of S. Right, so that will remove all the singleton, all the AIs, and then include all the 2 intersections, remove all the 3 intersections, and so on. Right. So here maybe I should say size of U plus this thing. Does this make sense, or people are still not sure about this? Why this should be plus and not a minus? Okay, so people looks like people are fine with that.
I am little
Yeah.
doubtful about this notation. Could you go over it once?
Okay, so size of U should be okay. Here I am running over all the non-empty subsets of 1 through m. Right, so I'm putting these AIs into a set, right? A1, A2, A3, and so on up to AM. Right, so I'm putting these sets into a set. I'm not constructing the union, I'm putting all of them in a set. Okay, and now I'm going over all possible subsets of these, right? Maybe this subset, and so on. And depending on the size of the subset, I decide whether I want to include the size of the intersection of these AIs or I want to exclude it. Right, so we'll take a concrete example. We'll take an example where m is like 2 or 3 and see what the statement says. Is that okay?
Okay, sir.
Yeah. So let's take an example to understand what the statement says. Right. So for example, if your m is equal to 2, right? So the situation is this. So let me just copy it. Right, so this is what you're looking at, and now in case of m equal to 2, you know what is the size of U minus A1 union A2, right? So this is size of U minus size of A1 minus size of A2. But now what is the problem? You have excluded the intersection of A1 and A2 twice, right? So if you look at this expression on the right, everything over here gets counted once, everything over here gets counted 0 times, everything over here gets counted 0 times, but everything over here gets counted -1 times, right? So how do you fix that? You just add the size of A1 intersection A2, right? Okay, and now if you look at this summation, right? So this is the size of U term. This corresponds to the set S is equal to the singleton 1. This corresponds to the set S is equal to singleton 2. And this corresponds to the set S is equal to 1, 2. Okay. So similarly, if I take the example of m equal to 3, what do we have? Right, so if you have m equal to 3, right, so now size of U minus A1 union A2 union A3, what is this equal to? If I just take the size of U, I'm counting all elements once. Fine, so I don't want elements which are in either of A1, A2, A3. So let me subtract size of A1 minus size of A2 minus size of A3. Now what is how many times is each element getting counted? Elements over here are getting counted once due to the U. Elements over here are getting counted 0 times. Elements over here are getting counted -1 times. Right, and elements over here are getting counted -2 times. Right, is that correct? So A1 intersection A2, right? So if an element is present over here, then it is getting counted once over here, and then it is counted -1 times and -1 times. So it's overall it's -1. And similarly over here, it is getting counted once over here and then subtracted thrice, so it is -2. Right, so how do we fix this? Let's start adding the sizes of the intersection. A1 intersection A2 plus size of A, right? So as soon as I add size of A1 intersection A2, what happens? right? So this becomes 0, this becomes -1, all right. Plus size of A1 intersection A3, right? What does that give us? That makes this 0 and this 0, and then you need to fix this, so you add in A2 size of A2 intersection A3. What does that do over here, right? So that makes this 0 and it also makes this 1, and then to fix this 1 you just subtract the size of A1 intersection A2 intersection A3. Right, so now everything is good. Okay, and now if you were to again relate this with this expression in red, right? So this size of U, this corresponds to the set S being equal to 1, this is just 2, this is the set 3, this is the set 1 2, right? So I hope you are getting the idea. Is that okay?
Yes, that's fine.
Okay, any other issue with this notation? I don't want that to be a kind of hurdle in understanding the principle. Okay, fine. So let us try to prove this. Okay, we are going to present a slightly informal proof which is more intuitive but not as rigorous. And I'll tell you how to write a rigorous proof. I'll just give you a hint and leave it for you to figure out. Right? So we'll just look at the high level idea, intuitive proof, and I'll leave the rigorous proof for you.
Sir?
Yeah.
In this A1 intersection, A2 should be null set, right?
What do you mean?
If A1 is the set 1 and A2 is set 2. So
No. That's not what I'm saying. That's not what I'm saying. So where do you get this term from? You get this term when you substitute S is equal to the singleton 1 in this expression. Right? So maybe S is equal to 1 over here, S is equal to 2. S is running over all subsets of 1, 2, 3, which are non-empty. Right?
Okay.
Yeah. Now is it okay? All right. So let us do the proof. Yeah. So the proof idea is exactly the same as what we said over here, right? So you look at all possible kind of regions over here that are created in the Venn diagram. If you were to imagine the Venn diagram over n sets, right? And then for each region, you argue that for every element in that region, that element gets counted exactly as many times as it should get counted. Okay, if it is outside all the AIs, then it gets counted once. If it is inside any of the AIs, then it gets counted 0 times. Right? That's what we'll argue. Okay. Okay, so let me copy this on the next slide so that it remains in front of our eyes. Proof. Right, so okay, we prove that if X belongs to the union over all I equal to 1 through M AI, then X is counted 0 times on the RHS and if X does not belong to the union, then it is counted ones on the in the RHS. Right, so how do we do this? So suppose, right, so suppose consider an arbitrary x in the set U. Okay, so now we want to classify these elements depending on which regions they lie in. Right, so let us look at all the AIs which contain this set X. Okay, so let T be the set of all I such that X is in AI. Right, so go over all AIs, right, and record the indices of all sets AI which contain the element X. Right, so what do we want to prove? We want to prove that if T is empty, then X is counted once on the RHS, and if T is not empty, then X is counted 0 times on the RHS. Is everybody with me up to this point? Okay, cool. Everybody seems to be with me. Cool. So now, right, so number of times X is counted in the right hand side. Right, so what are we doing over, right, so this size of U is going to count X once, right? So this is equal to 1 plus summation over something. When is X going to get counted over here in a generic term like this, -1 to the power S intersection of AIs? Right, so X will be accounted only when X belongs to this intersection. Right, so for X to belong to intersection, right, so okay, so let me just write it that way. So S subset of 1 through M, S not equal to empty set, and X belongs to the intersection of AI I in S. Right, so for each such S, the element X will be counted, and how many times will it get counted? It will be counted -1 to the power size of S times. Right? Is everybody with me up to this point?
Excuse me, sir.
Yeah.
Sir, here can't we just say that S is a subset of T?
Exactly. So that is the next step, right?
Oh.
That is exactly the next step. So when does X belong to this intersection? Right? Sorry.
Sir, could you explain the last line?
Last line as in this line?
Yes, sir.
Yeah. So, right. So we are going over all the terms in this expression one by one, and then we are only considering the sets which contain X. Right. So U obviously contains X, and therefore this term size of U counts X once. Are you with me up to this point?
Yes, sir.
Yeah. So now when does U get counted in this set? When does this, right? So when does X get counted in a term of this form? Right. So that will happen if and only if X is in this set intersection of I in S, AI. Right. So which is why I put that constraint over here. Summation over all S not equal to empty set, and only those S such that X belongs to the intersection of AI's I in S. Okay. Is that okay, or is there
Yes,
still a problem? And then how many times is X counted in this kind of a term? -1 to the power size of S times. Okay. Cool. So now as somebody said, so X belongs to the intersection of AI. I belongs to S. So this condition, this last condition, right? So this last condition, X belongs to intersection of I in S, AI. So this happens if and only if S is a subset of T. As soon as S contains some I which is not in T, that corresponding AI is not going to contain X, and therefore the intersection is not going to contain X. Right? So therefore this is equal to 1 plus summation of -1 to the power size of S where S is a subset of, I can just write S is a subset of T now. I don't need to mention S is a subset of 1 through M, and S is not equal to MT. Right, so I can put this together in a clean manner. I can just say this is summation over S subset of T minus 1 to the power size of S, right? Because this I can say that this corresponds to the term S is equal to empty set. Is this okay? Now, does somebody already see the argument? Yeah, Vedant.
So then we can maybe choose number of elements from T, like NC2, when we want size of S to be 2, like that.
Sorry, say that again.
Sir, then we can choose elements from T. When we want size of S to be 2, then we choose 2 elements from T. So size of mod T C2, like that.
Okay. But is there an easy way, Abhinav?
So there are two cases. Either X belongs to this union 1 to M AI, or it does not belong. Now, now if X belongs to this union I equal to 1 to M AI, then there exists at least one I such that X belongs to I. Hence T is not empty. T is mod T is greater than or equal to 1. Then in that case, this term here, sigma S is subset of T minus 1 to the power S. So S, the number of subsets of T will be 2 to the power mod T.
Correct.
So, and since mod T is greater than 1, this term has to be even. And hence this entire summation becomes 0.
Okay, you are almost there. You are missing one little bit of explanation, right? Ramanuj.
Sir, the other case is okay.
Yeah, the other case is okay. The other case is easy, fine. But in this case where X belongs to the union of AIs, there is one little explanation that you are missing. I mean, I agree that this is even, but why is it equal to 0?
Sir, this was what we did yesterday, NC0 minus NC1. Yes.
Absolutely, right? So what did we do last time? We said that if you have a non-empty set, then its even size subsets are in the bijective correspondence with its odd size subsets, right? And somebody already gave that correspondence, right? Where S goes to S XOR some element. Okay, so that is a bijection. So we'll use that now. Okay, so if X does not belong to the union of AIs, I equal to 1 through M, then what happens? Then T is equal to empty set, and therefore number of times X counted on RHS. So therefore, since T is the empty set, S can only take the value empty set, right? So this is equal to minus 1 to the power 0 is equal to 1. And if X belongs to union I equal to 1 through M AI, then T is not equal to the empty set. Abhinav, I'll come to you. Let me just finish this. And therefore, number of times X counted on RHS. Right, so let's split this summation depending on whether S is the size of S is even or the size of S is odd, right? So this is nothing but S subset of T, size of S even of 1 minus, right? So plus subset summation over S subset of T, size of S odd of minus 1. Right, and then this is 0 from last time. Last class. Abhinav, your hand was up.
So it was, I forgot to lower my hand.
Oh, okay. Right. So this is the informal idea. Any issues with this? Raise your hand and feel free to ask.
Sir, could you explain what was the idea in the last class?
So in the last class, what we did was the following result. So we proved that right? So you have, let's say you have some set T which is not empty. Okay, and I take the collection of all even size subsets of T. And I also take the collection of all odd size subsets of T. Right, so which one is the larger set and which one is the smaller set? Any idea? So this specifically for the person who asked the question. Can you say that one is larger than this other, or can you say both are of equal size always? Any idea?
So doesn't it depend on the size, or whether the size of T is even or odd?
It doesn't. That is the idea, right? So the claim is that they have the same size always. And why is that so? Because I can show that there is a bijection between them. Right? So because T is not empty, suppose some element X belongs to T. And now this bijection is as follows, right? So a set A will be mapped to the set A symmetric difference, the set X. Right, so I hope it's clear that this is a bijection, right? So two sets cannot get mapped to the same set. Everything has a pre-image, right? So I leave this for you to check. Everything has a pre-image, right? So what do we need to check? It's a 1-1 function, it's an onto function, and yeah, that's it. Right, and because there is a bijection between these two sets, the number of even size subsets of T and the number of odd size subsets of T are always equal, assuming that T is non-empty and T finite. Let me also add that. This doesn't make sense for infinite sets, although the bijection makes sense for infinite sets, but then it doesn't make sense to say that the number of even size sets is equal to the number of odd size sets. Abhinav, your hand is up.
Sir, you said that was an informal proof. So what should we write to make it formal? It looks like formal.
So if you want, yeah, I'm coming to that. I'm coming to that. Manthan, what is your question?
Sir, this proof, can we do this by induction on M? Because when we don't know the formula, we write A1 union dot AM equal to A1 union AM minus 1 union AM. Like that.
Possibly you can do that. Yes, you could do that possibly.
That will be formal now if we do like that induction. I mean, if we'll try by induction.
If you try by induction, then what?
Then that will be the formal proof, no? I mean,
that yeah, depending on how you write.
Okay.
Yeah. So what we'll do? Okay. So yeah, the formal way of writing this proof is as follows. Manthan, your hand is still up. Is there a question?
No, sir. I forgot.
Okay. Cool. No issues. Okay. Fine. So let's get rid of this slide maybe, because that is something we did in last class. Right. So formal idea, let's again copy this on the next slide so that it is in front of our eyes. Okay, so this formal idea. So this is a usual trick. So if when you're trying to find the size of a set, try to divide it into more simpler sets and find their size, add it up. When you're trying to find the probability of an event, try to divide that event into disjoint smaller events, simpler events, find their probabilities, add them up. This is a generic idea, right? So what is the right? So yeah, so this set, right? So this set U minus, so the rigorous proof, right? So U minus A1 union AM, this is equal to, this set is equal to the union over all X in U, right? So look how I'm writing it. The same set U minus A1 union AM, and then now I'm going to intersect it with the set X. Right? So I'm using an extremely trivial thing, right? So if T is a subset of, all I'm using is if V is a subset of U, then V is trivially equal to the union over this U and union are kind of ambiguous. So let me just make this U, write this U this way. Yeah, so V is equal to the union over X in U of V intersection X. Extremely trivial statement, right? And moreover, this is a disjoint union, right? So no two of these sets are going to intersect. Well, so each of these sets is either singleton or just the empty set. Fine. So therefore, the size of this set is the sum of the sizes of these sets, right? So therefore, the size of U minus A1 union AM is equal to summation over X in U, the sizes of these sets, right? So each of these sets is going to have size 0 or 1. So let's see what happens, right? And this this set minus union, I can write it as an intersection U intersection A1 complement intersection A2 complement intersection AM complement intersection X. Okay, fine. And now what? Right, so I'll define, let us use the same T as before. So this is equal to 1. This set is 1 if and only if X belongs to all of these sets AI. So no, sorry, this oh no, what am I saying? When is this intersection non-empty? This intersection is non-empty if and only if acha. No, what do I want to say now? Okay. Okay. Right. So let's also work with the right hand side, right? So what is the right hand side? Right. So similarly, I mean, so this is the left hand side. So the right hand side is going to be equal to, by the same logic. So this U I can write it as, so this U, let me just write it as U plus summation over, right, X in U summation over this S with all the constraints minus 1 to the size of S, and then intersection of I in S AI intersection X, right? Yeah, and now now the same idea will hold. So this intersection is non-empty if and only if S is a subset of T, right? So this size of U plus summation over X in U summation over right, S subset of Tx, right? So where Tx is the set of all I such that X is in AI, right? S not equal to empty set minus 1 to the size of S, right? So I'm essentially doing the same steps now. Summation over X in U, summation over, I can push this size of U into this summation by adding the S equal to empty set term, Tx minus 1 to the size of S, right? So this summation over X in U, right? So this guy is 1 if and only if Tx is empty and it is 0 otherwise, right? So this is summation over X in U and such that Tx is equal to the empty set of just 1, right? And which is precisely what we want. Oh, so actually, yeah, this step was not necessary. Yeah, so the idea is to split each of these sets, intersection AI, I in S, into simpler sets. Yeah, so yeah, before I publish the slides, maybe I'll clean this proof up a bit and then I'll publish. Is the idea clear? Right.
So you said that this is trivial. I mean, I didn't understand what the expression is that V equal to union Ola. Can you just explain? Just don't just in a one line or two line.
So basically what I'm saying is this is your U, this is your V, right? So what I saying, so I'm taking the union over all possible X in this set U of what? V intersection X. Now what is going to happen if X is actually in V, then this V intersection X will be just X, and otherwise it will be the empty set, right? So therefore this is just going to be disjoint union over all X in V of the set X.
Okay, so got it. Yes.
So that's why I said it's a trivial statement. Okay. Yeah.
What's that like plus symbol inside U? Isn't that the
So plus symbol inside U is disjoint union. So all okay. So basically okay. On one hand, it says that the left hand side is equal to the union of the right hand side. Union or as indicated by the union, right? And moreover, it says that the sets which you are kind of taking the union over are in fact disjoint. Okay.
So like it's basically like summing up kind of thing also, right?
Exactly.
Okay, sir.
Right. So when you say A disjoint union B, all you are saying is when you say C is equal to A disjoint union B, so this is same as saying C is equal to A union B and A union B is equal to the empty set. Okay. Yeah, I'll have to slightly clean this up before I share it with you all. Okay, should we move on? So if the statement itself is clear, right? So working principle, yeah, Vivanshu,
Yes, sir. You have written if V is equal to U. Sir, I think it should be V subset of U. Then V.
Yeah. That's what I meant. That's exactly what I meant. V subset of U. Yeah. Okay. Fine. So now let us pop off this problem from our stack. Which problem? The problem of counting the number of surjections from an n size set to an m size set. Right. So here we said that Q is the set of all functions from x to y. AI is the set of functions in which, right? So it's the set of functions f such that I does not belong to the image of f, or in other words, I does not have a pre-image under f. And now we exactly want this set, right? So this kind of completely pattern matches with the left hand side of the principle of inclusion exclusion, right? So let us see what we get, right? So counting right. So what is this going to be? Size of U minus A1 union AM, right? So this is going to be equal to summation over size of U plus summation over S subset of 1 through M, S not equal to the empty set of what? Minus 1 to the power size of S in S AI. Right. So now let us try to understand a generic term of this form. Right. So given if I give you a set I which is a subset of S, right? So remember this set 1 through M is also equal to Y. Right. So this is 1 through M. So this is Y, and now S is a subset of Y. What is really this set? Yeah, Ishan.
I wanted to ask that what was you said that the first proof is informal.
The first proof is what?
You said that the first proof is not formal.
I
want to ask what was wrong.
What was informal in it? What do I mean by x is counted 0 times or x is counted once in a particular expression? That is kind of undefined thing, right? We didn't formally define it. Okay, which is why I said it's an informal proof. Okay. So this is some intuitive idea that all of us share, right? But we haven't kind of formally defined it. What do you mean by x is counted 10 times in some weird summation expression? Okay. Yeah. So now what is this intersection I in S AI? What is this? What does this set really represent? What set of functions is this? What was AI? If you recall, AI is the set of functions, is the set of f going from x to y such that I does not belong to image of f. So what is this intersection? Somebody, come on. Right, so intersection of AI, I not belonging to S, it really says that you're looking at functions f in which none of the elements of S are in their image. Right, so observe that intersection I in S AI is the set of all f going from x to y such that what? Such that S intersection image of f is empty. Okay, is everybody with me up to this point? Raise your hand if you're not comfortable with this. Ankit, is this okay?
Hello, sir.
Yeah, I said, are you with me up to this point? Is this okay?
Yes, sir. Yes, sir.
Okay, cool. Fine. So now, does somebody want to tell me what is this size? Intersection of, right? So what should I, if I start substituting the sizes, what should I write over here? Right? So this is equal to size of u plus summation over S subset of 1 through m, S not equal to the empty set, minus 1 to the size of S. Well, size of u actually is what? M to the power n. What should I write over here? What is this size?
M minus size of S to the power n.
Absolutely. Right. So you want functions, right? So what is this set? It's the set of all functions of the following form. This is x, this is y, this is s, and you want functions whose image is disjoint from S. Nobody goes into S. Right, so for every element of X, you have m minus size of S many choices to on where to map it to. Right, so therefore there is m minus size of S to the power m. Right, so now I can write this in a more compact manner. So this is just m to the power n plus, in fact, let me just push this m to the power n inside. So this is just, right, so if I just substitute size of S equal to 0, I'll get m to the power n even in this term. So I'll just write this as S subset of 1 through n, 1 through m, minus 1 to the size of S, m minus size of S to the power n, and this is equal to, right, so this size, right, so this expression really depends only on the size of S, right? So therefore I can, instead of summing over S, I can write a summation over k going from 0 to m minus 1 to the power k. How many subsets of size k do I have? Well, I have mck subsets, m minus size of S to the power n. Oh, did I mess up the m and n or not? What was m and what was n? N balls into m bins. Yeah, so this is okay.
So at the end, it will be m minus k, right?
M minus k. Good. Okay. Any issues up to this point? Feel free to ask questions. All right, so we have something, although we don't have a compact expression, we have some answer to the question which which we asked earlier. What is the number of surjective functions from an n size set to an m size set? And let us take this back to its proper place. I hope this fits. Yeah, this fits. Cool. Okay. So now that we have this, can somebody suggest how do we fill some more of these? Let's say any of these two spaces. How do we fill in this space? Let's say. Right, so the number of ways, we have already found the number of ways of distributing n distinct balls into m distinct bins so that no bin is empty. But now the modified scenario is now the bins are identical. What do we do?
Sir.
Yeah.
Sir, here we can make A1 and A to AN, like now how many bins we are filling with?
Meaning?
Sir, that set A1, A2, AN in the principle we can relate those set with the number of bins we are filling.
Number of bins we are filling, but U minus union of AIs is not what you want really, right? What is U?
Okay.
Right, so it is okay. So okay, now the hint is okay. If you can do something using simple ideas, don't try complicated ideas, right? So now that we have derived this, the hint is you don't really need inclusion exclusion. Okay, Ishan.
I mean, the balls and bins are a made up distinction. So can't we use the second row to
Ishan, your voice is breaking a lot.
I'm saying that the balls and bins are a made up distinction. So can't we use the second row to write the third row?
Second row to what? I don't understand what you're trying to say.
So I think he's trying to say that we can think of bins as balls and balls as bins and use the second row.
No, yes. But no, the fundamental difference is two balls going into a single bin. That makes sense, but two bins getting mapped to a single ball doesn't make sense. Right, so it's not like symmetric case. Do you understand my point?
Yes, I got it.
Yeah, Vibhanshu?
Sir, the second column of the distinct balls, identical bins, I think that is easy to fill. We can just distribute M balls first into the M bins, and then the remaining we can distribute like the remaining balls will be N minus M. We can distribute them in M to the power N minus M ways, I think.
No, but Vibhanshu, the problem is the balls are distinct. Right, so so if you arbitrarily choose the balls which are kind of using initially to make the bins non-empty, then you might be overcounting things, right?
Yes, sir.
Yeah.
So I guess what he's trying to say is that when when first put a single ball in all the beans, then they not remain identical. I mean, we can judge a bean by the ball the first we put in. So after that, why can't we do that m ki power n? I mean, first choose m number of ball, then put it on the beans. Then all beans will not be identical anymore.
But then the problem is the following, right? I think I mentioned this last time also. So let me quickly mention it over here, right? So you have three balls. Let's say you have a red ball, you have a green ball, you have a blue ball, and you have two bins.
Yes, got it. That example. Yes, got it.
Yeah, did everybody get it? What is the problem with Vibhanshu's idea? Vibhanshu's idea is pick two balls. Sorry?
No, sir.
Yes, sir.
Please
Could you
start
explain
completely.
it?
Okay, Samar Singh, no, Samar Singh, yes. So let's do that. So what is Vibhanshu's idea? Right? So you have three balls, you have two bins. Vibhanshu says you pick two balls out of these three and you put them in the two bins. Right? So let's say I put red and green. And now you are back to the case where the bins are distinct, and now you want to put whatever the remaining distinct balls into distinct bins, right? But the problem I claim is, right, so let's say I first pick red and green to make the bins distinct, and then I put in blue into the red bin. So what I'll get out of this is same as what I'll get out of the following scenario. I use blue and green to make the bins distinct, and then I put the red ball into the blue bin. I'll get the same answer, which is why I said you're overcounting this. Okay. Abhinav, your hand is still up.
Sir, I think like what we should do is we should not choose now, since the bins are identical. So we should not choose. Like MCK term will should not be there. Rest should be same.
MCK term will not be there, but did I forget the power? M minus k to the power something, no? What was it?
It was n.
Sorry,
n.
M minus k to the power n. Oh, so maybe when I copied it, kind of I lost it somewhere. Lost that in somewhere. Let me first fix this quickly. N. Yeah. So now what are you saying, Abhinav?
So in this same expression, what we were doing, we were first distributing everything in the all, like we're checking all the possibilities. Then we said that there is one bin that is empty. Then we chose that bin which is empty, and then we distributed in rest bins, right?
No, I don't understand.
So this is what expression
So this MCK is really the number of, right? So you're looking at configurations where k bins are left empty.
But since the bins are identical, we won't have those configurations, right? It will be only one case.
Okay. So you want to start out with the all possible ways of distributing balls, and then you want to remove the ones in which n minus one bins are empty, n minus 2 bins are empty. But then if you are trying to compute the number of ways in which you put in balls so that exactly k bins are empty, you are kind of back to the same problem, no? You're essentially saying you want m minus k non-empty bins. How do you do? Right, so you're putting balls into m minus k bins, and you don't want any of them to be empty.
Oh, okay.
You're back to the same problem. Vidushi?
So we can consider the third part, column 2, as some function f, and we got the ways in which we can distribute distinct balls into identical bins. Now if every bin
let's call this
is
f of n,
distributed,
then what?
and if we distribute it now into distinct bins, considering them, like if we want to paint them now, then we can paint them in pictorial ways, and the compact expression will equal to the expression we just got by the inclusion exclusion principle.
So this this will be equal to this?
No, after multiplying with m factorial, after painting
after multiplying with m factorial. Okay. Cool. Nice idea. Yes. Kshitij, yeah, your idea is correct, Vidushi. We'll do that. Kshitij, your hand is up.
So I just had the same ideas with Vidushi.
Okay, fine. Good. Right. So this is the same idea as the idea we used to prove that NCK is 1 over k factorial times NPK. Right. So count the same the size of the same set in two different ways. Right. So this is an expression for the size of the following set. It's the number of ways to put n balls into m bins, so that no bin is empty. Where the balls are distinct, bins are distinct. Right, so that can be counted in another way, right? So let's take this up: distinct balls, identical bins. Right. So distinct balls, identical bins. No bin empty. right? So this is what we want to count, right? So, but another way of counting the number of ways to put n balls, n distinct balls into m identical bins. No, sorry, m distinct bins such that no bin is empty. Right? So what do? You first decide what groups of balls go into the same bin. Right? So this is my set of balls. I partition it appropriately into some subsets and then say that all these balls stay in the same bin, all these balls stay in the same bin, all these balls stay in the same bin, all these balls stay in the same bin. Right? So this is my first step. I partition the set of balls into some m parts. And then later I assign the bins to these. Let's say, so then I say that, okay, this set of balls goes into bin 1, this goes into bin 2, this goes into bin 3, and this goes into bin 4. Okay, so therefore this number of ways of putting n distinct balls into m distinct bins such that no bin is empty is equal to number of ways to put n distinct balls into m identical bins such that no bin is empty. Right, so first do that. Take some m identical bins, put those balls, distribute those balls into those m bins so that no bin is empty, and then now you decide which of the identical bin goes to which of the distinct bins. Right, so therefore this times m factorial. Right, so the number of ways to put n distinct balls into m identical bins such that no bin is empty is just 1 over m factorial times this, the earlier number that we derived. Is this okay? Is this absolutely clear?
Sir, then why did you say that we do not need inclusion exclusion here?
We don't need to apply it once again. That was what I meant.
Oh, acha, okay.
Okay. Yeah.
Sir,
yeah.
So like I guess that this is correct, but how do we know that this is correct? Like in the previous cases, somebody was giving some functions that we could give a counter example, so we said those were incorrect, but like maybe this satisfies our intuition and we feel it is right, but it is wrong. Like I know that this is correct, but I don't use the rigor.
I see. Right. So basically, we want to construct two sets in which such that there is a bijective correspondence between them, right? So maybe the two sets. Yeah, let's try. Let's see whether we can prove this formally. Okay. Right. So this set is. Right, so this number of ways to put n distinct balls into m distinct bins such that no bin is empty, right? So this is the set of surjections from 1 through n to 1 through n, right? And then this second set that we are looking at is really the Cartesian product of two sets. This is a set of partitions of the set 1 through n, set of permutations of 1 through n. And now we are trying to prove that there is a bijective correspondence between the two. And what is the bijective correspondence? So given a surjection, right? So given a surjection of this form, right? So what do you want to prove? That there is a bijective correspondence between this and this. So given the surjection, I need to construct a pair. The first component of the pair is a partition of 1 through n, and the second component is the set 1 through m. Okay, right? So now the partition is natural. So this is my partition, right? I say that two elements are in the same part if the surjection maps them to the same element, right? And then the set of permutations is the following, right? So now that I have found the partition, I can label each part of that partition in a systematic manner. The first part is the part which contains the element 1. The second part which contains the least element which is not present in the first part. The third part is the part which contains the least element which is not present in the first two parts, and so on. So this way I can systematically number the parts. And having numbered the parts, I want to say that, okay, how do I map them to the exact elements, right? So that can be done in m factorial ways. Okay, right? So each part, there are m, yeah. So there are, you think of each part as a person and think of the m elements over here as chairs. I want to place each person into one chair. So that's m factorial. Prabal?
Sir, could you repeat your idea again?
Sorry?
I couldn't get you. Sir, I couldn't get this.
Okay, I'll do that. Okay, fine. So yeah, so the question was how do we prove this kind of more rigorously? So we want to prove that we are going to use bijection, right? So we are going to have two sets with a bijective correspondence between them. The first set is the set of surjections from 1 through n to 1 through m, right? So the size of this set is exactly the left hand side of this equality. Is that okay, Prabal, up to this point?
Yes, sir.
Yeah. So now we want to construct a set whose size is equal to the right hand side of this equality, right? So since it involves a product, I will construct a set. I will take the Cartesian product of two sets. One set whose size is the first term and the second set whose size is the second term, right? So this second term is easy, right? What is m factorial? The size of which set? Natural set. The set of permutations of the of m elements. The number of ways of putting assigning m seats to m people. Okay, Prabal?
Yes, sir.
Yeah. And the first set is, I want to say that it is the set of partitions of 1 through n, right? Or the set of or the number of ways of putting n balls into m identical bins.
Yes, sir.
Yeah, the set of all possible ways of
partitions is like m partitions we have to create, right?
Sorry?
We have to create m partitions, right?
You are not, okay, so yeah, slight technical mistake with the way you said. You are building one partition. A partition contains m sets.
Okay, sir. Okay, yeah.
Okay, a partition is a collection of sets such that no two of the sets are intersecting and the union is equal to the set you are trying to partition. Okay, so now how do I establish the bijective correspondence between these two sets? The bijective correspondence is given by the following function. Given a surjection, I want to construct a partition and I want to find a permutation of 1 through m. Right? So, okay, let me slightly draw a better diagram over here. Let me actually take an example. Let's say you have 1, 2, 3, 4, 5, and you have 1, 2, 3 over here. Right? So let's draw some surjective function. Right? So given this surjective function, what will that get mapped to under this bijection? It should get mapped to a partition and it should get mapped to a permutation of 1 through m. It should get mapped to a pair. Right? So this function f will get mapped to the following partition. What is the partition? Right, so what is the partition? The partition consists of the set 1, 2, because they are getting mapped to the same element. 3, 5, 4. So this is the first component of the object this function f gets mapped to, and the second component is the following, right? So now, this is my part 1. Part 1 is the part which contains the element 1. Part 2 is the part which contains the smallest element which does not belong to part 1. So this is part 2. Part 3 is the part which contains the smallest element which does not belong to all the earlier parts. So this is part 3. Right, and now I want to decide where do parts 1, 2, and 3, how do they get mapped to 1, 2, 3. Right, so here my part 1 is getting mapped to 1, part 2 is getting mapped to 3, and part 3 is getting mapped to 2. So this part, and this set x, this set y, this set this part ID, and this is the y. Yeah, Ramanuj.
So from set of partitions of 1 to n, you really mean set of m partitions of 1 to n such that no partition is empty.
Partition, exactly. So set of partitions of 1 through n into m non-empty sets. Yeah, sorry. Yeah, I missed that earlier. Now is it clear?
So like just to confirm these, the permutations
one at a time.
Of the.
Yeah, only.
Sir, am I audible?
Yeah, only Ishan speaks now. Yeah.
I wanted to ask, how are we deciding that which part is mapped to which?
Right. So you're right. So look at this function, right? So where are 1 and 2 getting mapped to? They are getting mapped to 1. So which is why I said part 1 gets mapped to 1. What is part 2? Part 2 is 3 and 5. Where are 3 and 5 getting mapped to? They are getting mapped to 3. So which is why I said part 2 gets mapped to 3. Okay. Is that okay, Ishan?
Yes, sir.
Yeah, Shrimanti, your hand is up.
So why would this be m factorial? The second one, I didn't get it.
So you have m parts, and you want to assign them into to the m elements of y.
Yes, but they have different elements, right? Like how are we mapping this?
Right. So you're mapping all elements of part 1 to some element of y. You are mapping all elements of part 2 to some other element of y, and so on.
Yes. So then what we do? Like we map this then.
So how many ways can you do this?
Okay, so we are mapping the ID to the parts, right?
You are mapping the part IDs to the set y.
Okay,
right?
got
it. So you're kind of decomposing the surjective function into two components. The first component is a partition of the domain, and the second component is a bijection between the parts that are generated by the partition and the codomain.
Yes, sir. Fine.
Prabal?
Sir, I still don't understand how are we assigning part numbers.
Part number is simple. Part number 1, it's some systematic way, right? Some well-defined way. So one possible well-defined way is the following. Part number 1 is the set which contains the element 1. Okay. Part number 2 is the set which contains the least element which is not present in the earlier part. Part number 3 is the set which contains the least element not present in any of the earlier parts, and so on. Okay. Prabal, is that okay?
Yes, sir. Yes, sir.
Okay, cool. So we have found this answer. Right. So by the way, yeah, I forgot to mention that this, where is it? Yeah. So this number. Right. So let us write down this number quickly. So this is 1 over m factorial. Times the summation k equal to 0 to m minus 1 to the k, m choose k, m minus k to the power n. And this often denoted by this capital S of n and m. Right, so this is called the Stirling number of second kind. Right, and there is a reason why it is called the Stirling number of second kind, because there is something called the Stirling number of first kind also. If time permits, we'll see what that number is. Prabal, yes.
Sir, it was left out.
Vibhanshu.
Sir, I think we can now fill the first column easily in terms of the Stirling numbers.
Good. How?
How, it will be equal to sigma of k is equal to 0 to the number of bins.
Maybe let's use some different letter L because k is already here. L is equal to what? 0 to?
Yes, sir. 0 to number of bins, that is n. Stirling number of n comma 0, n comma L.
Nice. Nice. Right, so now you are trying to distribute n distinct balls into m identical bins, but now there is no constraint that the bin must be non-empty. Right, so what is the reasoning behind this, Vibhanshu? Vibhanshu, can you quickly tell why this is so?
Yes, sir, yes. Sir, we can now distribute the n balls in 0 boxes, that is obviously 0, and n balls in 1 bin, that is such that no bin is empty. We can include
so what principle are you using? You're just using the addition principle, right? How many bins are non-empty? The number of non-empty bins can be 0, 1 through 2, 3 up to m. And if the number of non-empty bins is L, then the number of ways of placing distinct balls into those non-empty bins is S of NL by definition.
Yes.
Sir,
Vedant?
Sir, we'd also multiply this with MCL, right?
Why?
To choose the L box, L bins.
Bins are identical. Bins are identical.
That's right. Bins are identical. Oh.
Yeah,
Yes.
Ramanuj?
Sir, I think it would be helpful, I think, in the next class that you can explain why we can't use the same divided by m factorial in the m to the power n divided by m factorial here as well. Because, you used it.
Where as well?
Like, like, for example, distinct balls, identical bins is equals to distinct ball, distinct bins divided by m factorial.
Acha. Here, why can't you use?
Yeah.
Okay, so maybe remind me in the next class. Remind me in the next class. That's your job, Ramanuj. Okay.
Okay, sir.
Yeah. Okay. Cool. Fine. So we'll do that. All right. Any questions before we say tata bye bye? Yeah, Vidushi.
So the same thing you explained in previous class by explaining that the partitions can be identical, right?
Yeah, so but maybe Ramanuj wants some more explanation, so we could do that. Or if Ramanuj is the only person who wants an explanation, maybe you should ping me. Right, so the question is, why can't you just divide by whatever 1 over m factorial? Why can't you go from this column to this column by dividing by 1 over m factorial, by multiplying with 1 over m factorial, whereas you could go from here to here by dividing by m factorial? What is the difference?
Like in that distinct ball, distinct bin, like because if the empty parts would be same.
No,
right?
no. My question is raise your hand if this is not clear. Why it was okay to divide by m factorial over here to go from here to here, but why it was not okay to divide by n factorial to go from here to here? Okay, so it was not clear to Prabal, Aryan, Kushagra. Is that it? Okay, so there are some people. Okay, fine. So we'll do that in the next class once again quickly. All right, no issues. Fine. Chalo. So see you in the next class, which is on Thursday. Or actually, we could do it in the tutorial if you don't mind. Okay, chalo. Fine. See you on Thursday.